compression members, tension members we have considered, but actually they are each chapter, but they have compressed it to get only in 2 chapters all this. So again, beams is also included in the first chapter, but it is actually a separate one. They don't know this is a separate one. They are included in the first unit, that is bolted and welded connections. Okay, we'll consider the beams. So beam is a structural member. Mainly it resists the external forces by means of bending and shear. But you know already in the case of RCC, same area also will get beams. So length is larger, that one dimension larger than other 2 dimensions. That is the cross section, subjected to lateral loads. That is the vertical loads or horizontal loads. Gives rise to bending moment and shear forces in the member. So this is in case of beams. Purlins. Purlins means these are the members used in the trusses in case of truss roofs. So over the trusses, a purlin will run from one truss to other truss, over which sheets, covering sheets, roof covering sheets will laid. So purlins which rest between the trusses and support the roof sheets and beams are beams. They are considered as beams. But the load is going to act at particular places on the trusses. So for this, angles or channels are commonly used. T-sections are also used in case of water tanks. Also, this will be used for support steel plates. So in buildings, I sections are commonly used as beams. That is rolled steel sections. So if its capacity is insufficient, then plates are welded to the flanges of the rolled steel section. So that are known as the built-up sections. And there are 2 types in this. One is laterally supported beams. Another one is laterally unsupported beams. So in your syllabus, you are having only laterally supported beams. What is the difference between the laterally supported and laterally unsupported means? Suppose if you provide a I section, rolled steel section as a beam, so it will be subjected to vertical loading. And if you consider as a roof slab, so the roof slab will prevent the tilting of that I section, so that its load carrying capacity will be more. Suppose if you do not provide laterally unsupported, suppose if you provide laterally unsupported beams, then it will get deflected out of its original position. So horizontal forces may cause displacement of the top flange. So that is that reduces the load carrying capacity of the I section. So that is the difference between the laterally supported and laterally unsupported beams. So in your syllabus, you are having only a laterally supported beams. That is, lateral deflection is prevented. So generally, you will get, if it is subjected to vertical loads, so vertical deflection, downward deflection, you may get. But sometimes, suppose horizontal forces are acting, so it may get tilted. So the horizontal deflection also takes place. Due to that, load carrying capacity of the beam will be reduced. So we'll provide lateral support to the beam so that load carrying capacity is increased. Here it is given, if the compression flange and or the compression flanges are laterally supported, compression flanges are laterally supported, by flooring, that is the roof of the slab, the roof of the room, it is mainly subjected to bending and shear. If the compression flange of the beam is not laterally supported, the lateral buckling of the compression flange takes place and reduces the load carrying capacity of the beam. That is the difference. Flange is tilting of the top flange is prevented in case of laterally supported beams. That is the main difference between laterally supported and laterally unsupported. In the case of laterally unsupported, tilting of the flange may occur in the case of laterally unsupported. But in the case of laterally supported, tilting of the top flange will not occur. That is the difference. So the guidelines are given in the IS 800. Now, one more thing. So far, we are considering only elastic design. That is, the stress in the member is not going to exceed. We are using the stress within the permissible limit only so far. But here, the plastic moment capacity up to plastic moment capacity will go. So consider a cross section of a simply supported beam where bending moment is maximum. per given loading. Within the elastic limit, stress varies linearly. That you know, compression and tension. In compression and tension shown in the figure. Inga join aitunaru. So if you consider this diagram, within the elastic limit only we are considering the stress. Now we'll consider beyond the elastic. That is lower yield point, upper yield point, and plastic range will be here. After this plastic range, small value is there here. Then strain hardening stage will come. This is the strain hardening. The dotted line is the strain hardening. In between the elastic limit and starting of the strain hardening, plastic range will be there. That we will consider. So, if the load is gradual increase on a simply supported beam, the stresses also increases in the cross section. So, if you consider this simply supported beam subjected to UDL, this is the cross section of the beam. This is the stress diagram. Here, the extreme fibers are getting the stress first. This will be the neutral axis. So, where the maximum stress will be there? The layers at the extreme distance from the neutral axis will have the more stress. So, this is on the more compressive stress, and this will have the more tensile stress here. So, this occurring stress is less within the elastic limit. That is, it should not exceed yield value of the structural steel, that is less than Fi. Yield stress is Fi. Suppose if it goes on increasing the load, what happens? The stresses in the extreme fiber reaches the yield stress. So here you have got extreme fibers are reaching the yield stress Fi and Fi, both at compression layer, and this is the extreme tension layer. This one. Suppose if you further increase the load, what happens? So here the stress will be Fi at the extreme fibers, and within this below this extreme fibers and above this extreme fibers, the stress is less. Again. So this is the stress diagram. So if it is subjected to some loading, the stress in the extreme fiber will be more here. Extreme fibers, the tension and compression. At the top it is compression, the bottom it is in tension. Suppose if we further increase the load, the stress reaches Fy in the extreme fibers, in compression and the bottom at the tension also. So after reaching the yield stress, if you further increase the load, what happens means the extreme layers will have the yield stress same. They are in plastic stage, starting of the plastic stage here, both in tension and compression. And if you further increase the load, the extreme fibers will have the yield stress, and the inner fibers which are having the stress less than Fy, they are attaining Fy. So if you observe this this fourth diagram, this stress diagram of 3, so D, if you consider the D diagram here, the inner fibers are getting yielding, whereas the extreme fibers are remaining with Fy. So that is the main consideration in the case of plastic analysis. So if you further increase the load, so all the fibers will have yield stress Fy. So this is the stress diagram at the plastic stage. That is, the entire section has got a plastic stage. That is, all the cross section has got yielded. That one yielded means attain the stress of Fy. Fy form the entire section. So that will be act as a plastic hinge that will permits rotation without increasing the load. So if you observe here in the diagram, this is the small dip is there here. This is the plastic range, this one. So lower yield point, upper yield point, and then stress drops down, and then starting of the plastic range will come. So small range is there here. That is the plastic zone. After the plastic zone, the strain hardening zone will come. This one dotted line is the strain hardening zone. See, in the plastic zone, what happens means without increasing the load, after attaining the section, completely stress of Fy yield stress, it will continues to rotate without increasing the load. So that case will occur. So that is the criteria for plastic design. So ఇప్పుడు ఎలాస్టిక్ డిజైన్ లో ఉందంటే ఏమవుతుంది, ఎక్స్ట్రీమ్ స్ట్రెస్సెస్ వచ్చి లెస్ దాన్ Fy. So that is, you are not completely utilizing the section resistance. But in the case of plastic analysis and design, so our entire section will got a stress of Fi, which is a fully plasticized section. Up to that, we can increase the load. That is the difference between the elastic analysis and plastic analysis. So this is the plastic analysis. The same thing is given here. Hello, Babu. Mute. So this moment capacity is called plastic moment capacity of the section, and it is denoted by MP. So MP అని మనం రిప్రజెంట్ చేస్తాం. సో ఇంతకుముందు ఏమి బెండింగ్ మూమెంట్ అని చెప్పి కన్సిడర్ చేస్తుంటాం మనం ఎలాస్టిక్ లిమిట్ లో. Now in the case of plastic analysis, we'll represent with MP, plastic moment capacity of the section. Now, what is the area that is in the compression zone and tension zone? For any, it may be a rectangular one, rectangular beam or I section, anything, or channel section, or any irregular cross section, any section of the beam. So what is the area of the compression and what is the area of the tension that we will consider? So let the area of the section in the compression is AC, that is above the neutral axis, and the area of the section in tension is AT, and A is the total area. So equating the horizontal forces for the equilibrium condition, we get compression area into stress in the compression. So if it is in equilibrium, then force of compression equal to force of tension. So force of compression ఏమవుతుంది, area into stress, అంతే కదా. So area, compression area, that is above the neutral axis into stress. Stress is the entire section above the neutral axis has got Fy, and the stress, the area, the force below the neutral axis. The force below the neutral axis is the tension. So tension area into stress. So AT is the tension area below, that is below the neutral axis, into stress is Fy, because all the fibers have got yield stress. So Fy is same here. Fy get cancelled on both sides. Then area of compression equal to area of tension will occur. So area of compression equal to area of tension epudu avutadi, that is total area by 2 unnapude avutadi. So that is the case here. So when the section has fully plasticized, then area of compression equal to area of tension. That is A by total. If the total area is A, then A by 2 will get. Area of compression is A by 2 and area of tension is A by 2. So total area is A. So that is the same thing is represented here. So this is a case of rectangular section. So here the force of compression is going to act at G1, center of gravity, and at G2 the force of tension is going to act. This is for a rectangular section. So distance from the neutral axis is y top, here it is given. And this is the neutral axis, horizontal one. And G2 is the distance of CG of tension zone, and y bottom is distance from CG of the tension zone to this neutral axis. So when ASC equal to AT equal to A by 2, that is neutral axis divide the entire section into 2 equal halves, then it is known as equal area axis. So when a section has fully plasticized, then you can represent the neutral axis as equal area axis. So because it divides the total area into 2 halves. Here also this is for an I section. So y top is the distance of CG of compression zone to neutral axis or equal area axis, and y bottom is the distance CG distance of the tension zone to the equal area axis or neutral axis. So this is in the case of T section. So plastic moment capacity may be found by taking the moment of horizontal forces about the plastic neutral axis. It may be noted that total moment of resistance is the additive of moment of resistance by compressive force and tensile forces. Since the moments are of the same sign, these examples are solved illustrating the method of finding the moment and ZP. So in the case of bending moment formula, we are having M equal to F into Z. So in the earlier case, elastic bending moment we are considering. Elastic bending moment equal to Fy into ZE we are considering. Z elastic. Same formula is used here also. MP equal to plastic moment capacity equal to yield stress into ZP. ZP is the plastic section modulus. So plastic section modulus, this you will get values, particular values for shape of the section that are given in the IS item. So ZP is of the order 1.125 to 1.14 times Z-axis for I sections, and it is 1.7 to 1.8 for channel sections. Roll shield sections are treated as sections with uniform sections. It is possible to determine ZP values. So roll shield sections, you have ready-made values for ZP. So another thing is, suppose simply one more thing. Well, how many number of plastic hinges are required to fail a beam? That is the main thing. If you consider a simply supported beam, that is a determinate structure. So where the plastic hinge will form, it is subjected to external loads. If the simply supported beam is subjected to external loads, where the plastic hinge will form? The plastic hinge will form at the section where the bending moment is maximum. So if it goes on increasing the load at one point, you get maximum bending moment. At that point, the plastic hinge will form. So determinate structure అయిన తర్వాత ఒక plastic hinge form అయిందంటే then it will become plastic mechanism. So here a proper cantilever is there. Degree of indeterminacy of this one proper cantilever is here two reactions on this one and two equilibrium equations. So one is the degree of indeterminacy. So first plastic hinge will form here at the fixed end. So it will become a determinate one. So after forming the determinate structure, one more hinge forms where the bending moment is maximum. Then plastic mechanism will take place. That is the failure of the collapse mechanism will take place. So determinate structure plus one hinge. So to make the determinate structure, this one proper cantilever, one hinge is required at the fixed end. If one more hinge is formed at the point where maximum bending moment is there, then the collapse of the structure will take place. That is the collapse mechanism. This one is. So other things are there related to beams, frames, sway mechanisms that are not included in the syllabus. Sway mechanism, beam mechanism, combined mechanism like that. So you are using only beam, so consider only beam mechanism. So determinate structure form అయిన తర్వాత if one more hinge is formed, then plastic collapse of the structure will take place. That much only. So if we consider a fixed beam subjected to vertical loads, so degree of indeterminacy of this one is 2. So two reactions at the one fixed end, another two reactions at the fixed end other end. So total 4 and available equations are 2. So 2 is the degree of indeterminacy of this fixed beam. So it will form a determinate structure by forming the hinges at the fixed ends. So first determinate structure will form by forming the hinges and permitting the rotations at the fixed ends. So once hinges are formed at the fixed ends, it will become a determinate structure. And if one more hinge is formed at the point where maximum bending moment is there, then collapse of the structure will take place. So this is the consideration in the plastic analysis and design of structures. So this is the main theory. Any clarification, further clarification in this one? So you are in the elastic analysis, you are considering bending moment equal to Fy into Ze, yield stress into elastic section modulus. Next, in the case of plastic analysis, you are considering plastic moment equal to Fy into Zp. So Fy is the yield stress, Zp is the plastic section modulus, and Mp is the plastic moment capacity of the section. So this is only simple one, this one. So and one more consideration in this one is the neutral axis become the equal area axis. That it divides the entire cross section into two equal halves. That is area of compression equal to area of tension. That is another consideration in this. So equal area is known as neutral axis is considered as equal area axis. And this equal area axis divides the entire cross section into two equal halves. Area of compression is total area by 2 and area of tension is total area by 2. We can locate the equal area axis. Location of the equal area axis. The area of, considering the area of compression are equal to area of tension, and also you can take moments about this equal area axis from one end. So if you do problems in this one, we can observe how the equal area axis can be located. Here the one problem is there. Determine the plastic moment capacity and plastic section modulus. Moment capacity is MP and section modulus is